In this manufacturing plant, this particular machine, which is used for melting of iron ore, needs to be started on a daily basis from the start in the morning till the time the production is completed. This requires a regular maintenance as this is a very complicated and very heavy machinery. And if the machine does not start at the first go, there is quite an amount of fuel that is wasted, and this causes a lot of increase in cost. However, in order to understand what is the frequency that we need to ensure that the machine is maintained, we collect some data and we try to find out what is the optimum time that we need to run the maintenance for, so that the machine gives us a good return on investment in terms of the trade-off between between maintenance costs and startup in the first go. So let us have a look at the data collected. This is what the data collection results look like. Let's try to understand what's going on here. So this is the days gap of 1, which means this is a sample taken wherein the startup is measured after every day of maintenance. So today the maintenance is done, and then tomorrow the good startup is basically tested. If the startup is good, if it works in the first try, then we count it as a 1. Else we count it as a 0. So 27 random trials has been done, out of which in 26 cases the machine starts up at the first try, right? Which means out of these 27 days, there was only one day in which after the first day of maintenance, the machine did not start at the first go. In this case, let's say the maintenance was done today. The first startup was tested after 2 days. If the machine did start, then this was counted as an event, as a positive event. And if it didn't start, it was counted as a negative event. So 18 trials were conducted, out of which there were 12 positive events, 12 good startups on the first try. And 6 of them did not, in 6 cases, the startup did not happen in the first try. So this experiment has been continued and till 11 days. And if you can see the result here, obviously I think we can very easily observe that the closer the maintenance is to the trial, the higher the probability of a good startup. In fact, after 6 days, there is actually 0 good startups, which essentially mean that 7 days or more, if we wait after maintenance, then the probability of a good startup is almost 0. Now let us use this data to generate a binary logistic regression model, and let us study the model and check assumptions and fits. So I will go to stat regression. This is where your linear regression models are. Here I could have gone to binary logistic regression, but I will go to binary fitted line plot. So here I put under event, I put event, which is the good startup, and then the number of trials is basically the number of random samples I took, and the predictor is the days gap. So basically whatever number of days after maintenance we test the good startup, that will impact whether the good startup happens or not. So here we're trying to test the relationship between the days gap and whether the event of good startup happens or not. So it is an impact of the probability of the event, right? Let us look at the graphs. We need to check the residuals of this model. So 4 and 1 I have selected here. Please note these are deviance residuals. These are not your linear residuals that we see in linear regression. And then under storage, I will look at event probabilities or fits. I click OK, and it generates two sets of graphs, and also it generates an output. Let us study them one by one. If you look at the deviance residual plots for the event, the normal probability plot indicates that the residuals are fairly normal. If you see, the points are hugging the line and they are quite close to the line. I don't think there's an outlier. The histogram residual is also, it seems to be fairly symmetrical and centered at 0, if you see here, right? The fitted values, I don't see any indication of heteroscedasticity. It seems to be fairly spread out around the mean of 0, which again is a good sign. And in the observation order, again, I don't have a lot of points here, but it seems that there is no special cause, or there is no cause of concern. The data is fairly random. Okay. Now let us have a look at the graph. This is the binary logistic regression, the binary fitted line plot that the model has generated. This is the equation of the event. So this is an exponential, this is a logit model basically, and it shows a very nice smooth curve here. If I look at the individual data, you can see on the left hand top corner. So if the number of days after maintenance is 1, which means after every day of maintenance a good startup is tested, the probability of a good startup is somewhere around 88%, right? And it will drop drastically if I change the number of days to 2. It comes to somewhere around 75%, and so on and so forth. It drops quite sharply and then it kind of plateaus off. So after 6 days, around after 6 days, it's more or less around less than 1%, right? Alright, so let us have a look at the session window output. I'm going to maximize the screen here, and it gives the basic information like what is the function. So I have used a default logit function, and then if you see, the overall regression p-value is 0, which indicates that the regression is significant. And since it is one variable, we can expect that the 2 will be always same. In terms of looking at the deviance r-square, 78.79, it explains the variation in the data fairly well, close to 80%. We don't need to look at deviance residual r-square adjusted, because we are not comparing models here. It's just one model with one variable. AIC, again, a Kaike information criterion, it is used to compare models. When we have two models with different number of variables, the one with the lower AIC actually wins. But here we are not doing that. So it is giving the additional information such as what is the odds ratio, 95% CI, and then the equation comes over again. One thing to note is this particular, the first observation is considered to be a residual. It is beyond the 2 sigma line. That's 2.44 standard deviations from the center line. So this seems to be a big outlier. Other than that, the data points are fairly okay. All right. Let us have another look at the worksheet.